The universe is in a constant state of expansion. This ongoing growth was first observed in 1929. Scientists eventually came to understand that the elements making up our bodies were originally formed in the hearts of stars. By 1957, it became clear that the sky was more than a visually stunning display, it was a reflection of the universe's immense energy. There is so much occurring throughout the cosmos that we often remain unaware of most of it. We continuously ponder the reasons behind our existence, the formation of stars and planets, and the potential alternate paths the universe could have taken. In many cases, we don't address problems until they reach a critical stage, even if they are bound to affect us in the future. One example is Betelgeuse, one of the largest known stars visible in the night sky. It has recently started displaying signs of instability, showing noticeable trembling that suggests a significant transformation may be underway. Its immense size has long captured scientific interest so vast, in fact, that our Sun appears minuscule beside it. Betelgeuse is no ordinary star and never has been. It is a red supergiant, much farther from Earth than it seems, located over 640 light-years away. While this distance may not appear extreme initially, in terms of the universe, it is enormous. Even if we were capable of traveling at light speed, reaching it would take more than 640 years, a feat far beyond our current technological limits. In fact, with today's travel methods, such a journey would take more than 12 million years, a span that far exceeds the total duration of human civilization. This immense distance emphasizes the scale and force of this remarkable star, which has been experiencing intense quaking for some time. Though stars may seem serene from our point of view, they are often far from calm, regardless of their scale. The signals emitted by Betelgeuse are not yet fully understood by scientists. It has long been categorized as a pulsating red supergiant, meaning its brightness changes in repeating patterns that can last from 10 days to several hundred, depending on whether the star is expanding or contracting. These slow variations highlight the dynamic nature of the star. Betelgeuse's brightness fluctuates significantly, varying between a magnitude of 5 and 0, which is a notable difference for stellar objects. These changes follow cycles, the shortest lasting about 185 days, and the longest reaching approximately 2,335 days. Sometimes, the changes follow predictable intervals that can be measured with precision. In February 2021, for instance, a V-band value of 1.614 was observed, one of the dimmest recorded in recent memory, differing from Betelgeuse's typical luminosity. Beyond brightness, its deep red color is another striking feature, resulting from its surface temperature of around 3,500 Kelvin, much cooler than the Sun's 5,500 Kelvin. Although the Sun is smaller, it emits more energy per unit area due to its higher temperature. Consequently, Betelgeuse appears less radiant, despite being one of the largest stars known, though Betelgeuse has remained fairly steady for much of its life as a pulsating giant. It has recently transitioned to a more erratic state, which is concerning. The cause lies in its outer gas layers, beginning to burn as the hydrogen in its core becomes depleted. In red supergiants like Betelgeuse, this is a normal stage. As hydrogen fusion slows, the star's outer regions expand, making it even larger. At this point, helium begins accumulating around a core, mostly composed of hydrogen. A new process, called helium shell burning, begins where helium atoms fuse into heavier elements, like carbon and oxygen, releasing energy that counteracts the force of gravity, pulling the outer layers inward. However, unlike hydrogen fusion, helium burning is irregular and leads to sporadic energy bursts. These fluctuations can disrupt the star's structure, causing its outer layers to expand and contract. These motions appear to us as brightness variations over time. The resulting pulsations release significant energy, generating powerful stellar winds that blow vast quantities of material from the star's surface. This mass loss, a hallmark of red supergiants, alters how matter and energy are distributed within the star and impacts its development. As these layers expand and contract, a rhythmic pulsing occurs, observable as changes in brightness akin to a beating heart. To analyze these effects, astronomers rely on techniques like photometry and spectroscopy. Photometry involves measuring the star's light output over time, enabling scientists to detect variations in brightness. This is particularly useful in studying Betelgeuse, whose periodic pulses offer valuable insight into its internal workings. Spectroscopy, in contrast, examines light across different wavelengths, revealing key information about temperature and movement. When Betelgeuse pulsates, the spectral lines shift, offering clues about the processes behind the fluctuations. Together, these methods allow researchers to develop a fuller understanding of stellar activity by linking external changes in brightness to internal conditions. Astrophysicists take things further by using advanced computer simulations to model the internal structure of stars. These simulations use equations related to nuclear reactions and fluid dynamics to predict how the star's pulsations evolve in response to internal shifts. By comparing these theoretical predictions to observed data, scientists gain a deeper understanding of what is happening inside stars like Betelgeuse. One particularly fascinating internal process is stellar convection. This mechanism helps balance the star's internal energy production and outward light emission. In this process, hot material from the core rises, while cooler matter sinks, forming currents that move energy toward the surface. These internal motions affect the star's brightness, making it appear brighter when more energy reaches its outer layers. Variations in the amount of energy moving through these currents account for the periodic pulsations we see. These brightness changes are not random, but often follow consistent patterns. Betelgeuse, as a variable star, exhibits cycles tied to the repeated swelling and shrinking of its outer layers. As the star expands, its surface becomes cooler and dimmer. When it contracts, the surface heats up and brightens. This cycle results from the balance between two opposing forces, gravity pulling material inward and radiation pressure pushing it outward. The ongoing interplay between these forces leads to the star's pulsations and the resulting fluctuations in its luminosity as seen from Earth. Approaching the final phase of its life as a red supergiant, Betelgeuse shows increasingly intense pulsations and convective activity. As it nears the end of its nuclear fuel supply, it is expected to eventually undergo a supernova, a dramatic end for such a colossal star. Until that moment arrives, the pulsations created by internal convection will continue to influence its brightness, providing astronomers with essential clues into the inner workings of massive stars.